We continue with a series of lectures on basic physical chemistry for the Department of Chemistry, University of Lagos. In this video, we look at the dependence, the way the reaction, the enthalpy depends on temperature, and derive a formula to on this dependence. Usually, the enthalpy of a reaction is reported at a certain temperature. The delta H for a reaction depends on temperature, and it has been recorded for many reactions over a range of temperatures. In a situation where this is absent, the information for a certain temperature is absent, we may estimate the reaction enthalpy at an unknown temperature from its capacity and the reaction enthalpy at a reference temperature. This usually happens. Okay, so for example, let's look at a hypothetical reaction A going to B. Now, the change in enthalpy for this reaction is enthalpy of B minus enthalpy of A, and we know that we can obtain delta H using any method. If you differentiate this equation with respect to the T, we have the delta H dt is equal to the delta HCB dt, HB minus delta HA dt. So this is its capacity at constant pressure for B minus its capacity at constant pressure for A, which is just a change in its capacities at constant pressure. So we can say that the delta H dt is change in Cp. That's constant. So not for Cp, that's its capacity, molar its capacity at constant pressure. Or we can simply write the delta H is delta Cp dt. That's because Cp will also vary over a certain range of temperature. Okay, so if we integrate this expression, so we have integrating from the reference one, that is H1, to the unknown reaction enthalpy. So the reference enthalpy starts at so this is supposed to be T1 and this is to be T2. So T1, T2. So we have that delta H is, and depending on the expression for delta Cp, whether it's constant over the range of temperature or not, it can come out of the integral. Now this expression, please, this is T1 and this is T2. This expression is called the Kirchhoff's law. It describes the enthalpy of a reaction, the variation of the enthalpy of a reaction with temperature. And delta H1 is the temperature at T1, which is supposed to be here and is usually the reference temperature. And delta H2 is the temperature is the unknown enthalpy at temperature T2. That's the one we're trying to determine. And delta Cp is the difference between the molar heat capacities. So remember it's given in power. So if you multiply and if you have it given in other than in normal, then you have to multiply it by n. So for the products minus the sum of the Cp's for the reactants. Now if Cp is independent of temperature, which can happen when there is no phase change or if the temperature range is small, then it can come out of this expression and we simply add T2 minus T1. Again, this is T1 and this is T2. And then this will simply be H2 minus H1, delta H2 minus delta H1, and because of that we can bring H1 to this other side of the expression of the equation. So this is our Kirchhoff's law if Cp is independent of, is constant over the temperature range. Similarly, we have our internal energy, but in this case we have it as a Cv, because the U dt is the molar heat capacity at constant volume. Okay, so a quick example. The standard enthalpy of formation for gaseous H2O at 298 is 241. Estimate its value at 100 degrees centigrade, given the following values of molar heat capacity at constant pressure, and assume that the heat capacities are independent of temperature. So we have our reaction H2 plus half O2 going to H2O, and from the question, delta H is minus 241.82. So we are to determine the reaction at 100 degrees Celsius, which is 398. What happens? Okay, so let's see. At 398, so we have delta H2. This is our Kirchhoff's law. Apologies for this again. I think this is because I copied and pasted it. So this is T1 and T2. So because Cp is independent of temperature, so we have this equation that came out of the reaction. So Cp, delta Cp, which will be Cp for the products minus Cp for the reactant. So this will be half. It's corrected in the next line. So this is 33.58 minus Cp for hydrogen, that's 28.84, and half of Cp for oxygen, that's half times 29.37, and we have our answer at 9.9. It's important to note to always follow through with units. Our delta H is given in kilojoules, but we have our Cp in joules, so we have to convert it to kilojoules. So we convert it in a minute. The change in temperature is 300 degrees Celsius is 373. So 373.15 minus 298, that's 75.15. So if we multiply these two together, we get minus 747 joules per mole. And recall again that you have to convert this to kilojoules per mole, so we have it at kilojoules per mole. So that's 0.10. So we can now calculate our H2 at 373.15. So that will be the value at the reference point, which is 2 minus 241 minus 0. So this has to be converted because this is in kilojoules per mole. So our final answer is 247. Thank you.